we will have the third presentation by Dr. Dominic Laye. I hope I pronounce it correct, from the TU Delft and Delft Institute of Applied Mathematics. He will talk about the non-reactive and reactive simulations of a full-scale thermal oxidizer.
Thank you very much, Mr. Chairman, for the introduction. I would like to thank the organizers as a whole to be able for me to give a talk here. My name is Numerical. This is joint work with Marco Tadice. At Delft University, we have a large group of Chinese students that come visit us for our masters. I often tell them that I hope that one day I'll be able to give a talk in China. So here I am. Mission accomplished. I would like to talk about the energy transition and what the role has in energy transition of large-scale industrial furnaces. And today I'll present a test case of a vertical oxidizer. This is a device used to be able to do the combustion of flue gases that are being treated to be able to then release them or to release the combustion products into the atmosphere. So what you see here is a tower of about 30 to 40 meters high. In comes at the inlet a mixture of fuel and gas to be able to create a flame. And we also have the inlets of acid gas. So the acid gas is a product of from a process further upstream. We want to use the device over here to be able to do the combustion of the acid gases and get rid of them. So the device as a whole consists of 3 sections. A bottom part that functions as a chemical reactor. A middle part that is there to be able to recycle heat. Obviously the combustion will act as a heat source, so there will be heat generated, and maybe you want to reuse the heat in other parts of the process. And there is a top and final part of the process that acts as a stack to be able to then release the remaining gases at the outlet. Can I see a first video of the process? So what you I'm showing you here the results of the simulation. What you see here is a cross-section goes to the inlet, where you see the flow profile in 2 different simulation cases that I will discuss in the presentation. Takeaway message from the slides from this video is that the flow in the furnace is a transient process. So keep in mind that the flow doesn't reach in the tube a steady state. Can we also see the second video? So the second video shows you again a cross-sectional view of the velocity. Clearly again the flow is fluctuating still. There is no steady state being reached in the process. So this is my talk after the introduction that we just saw and discussion of the device. I want to talk about the open foam case setup and the solvers we use, and then get to the bulk of the comparison of the numerical results for two different settings of the maximum Courant number, and end up with conclusions. Okay, so we are in an energy transition. We want to say goodbye to the hydrocarbons and hello to the renewables. In this context, we can do different things. We can change the fuel, as discussed in the previous presentations, in which hydrogen is one of an obvious candidate, along with ammonia. There are ways to change the fuel and also change the oxidizer, maybe to reduce the nitrogen content of the gas, of the oxidizer. There are ways to enhance mixing. Maybe we talk to a company that injects the fuel laterally in the cylinder, and we want to maybe explore mild or flameless combustion regimes. All this is driven by a mixing process. So we assume the dump Coulomb number to be large, and therefore want to conduct first the non-reactive flow simulations. Focus of my talk today will be on the computational effort required to conduct accurate non-reactive flow simulations. Here we have more details of the device. We have an inlet consisting of a central fuel pipe, the red one. We have a blue region of air injection, so we have a normal diffusion flame. And we have an outer ring of nozzles in which the acid gases to be processed, are being injected. And we have views along the axis of the furnace. What you see here is a cross-sectional view of the mesh, and we have chosen to have probe points in the simulations to be able to do the post-processing. We'll talk about the probe points later. Here they are. Here we have a view on the mesh. When I talk to my students about mesh generation, I often joke about my contacts with NASA Langley, where I phone with NASA Langley to do mesh generation. In reality, I talk to Zagreb, and I talk to the developers of CF Mesh to get out a mesh for the device. What you see here is a mesh of about 2.5 million cells that are locally refined close to the inlets. And we also have refinements to be able to capture the boundary layers close to the wall. So this is a mesh generated using inside-out mesh generation implemented in CF Mesh. We hope soon to release the whole test case in a GitHub directory to be able to use this as a benchmark for future studies. Next is a slide about the flow conditions. We inject the gas, the oxidizer, and there's also a bit of a pilot in between. Important to notice is that, here we are, we have a cold air that carries the bulk of the momentum. Why is that? Because the air is the main driver of the flow. It will be important later to understand the pictures. We assume the fuel and the pilot to be hot. We do so to be able to simulate the presence of a flame even in the non-reactive simulations. Reynolds number of about of 100 million. So clearly a turbulent flow. It's incompressible and non-stationary. So we assume again that the combustion process is dominated by the mixing, turbulent mixing, and therefore we want to study the non-reactive flow. The combustion will come later, in the later stage. And we have the inflow of a central jet of fuel, a co-flow in annulus of a coaxial air inlet, plus the 8 nozzles to capture the inlet of the acid gases. It's an internal flow, so clearly the boundary matters. There is a heat release effect, turbulent incompressible flow. We will use the raw pimple foam solver from the ESI release of open foam. We therefore use raw thermal because there is no use here to use psi-thermal. Psi-thermal would be too complex here to use. And we use transonic off because, again, there is no compressibility effects will be taken into account here. Now I come to the results. I want to compare first a scenario in which I set on the inlets either a mass flow rate or a velocity on the pilot. And I will compare these two types of boundary conditions on the effect it has on the overall simulations. What you see in the graph is a comparison of setting velocity versus setting the mass flow rate. The graph on the left shows you what happens on the fourth probe point close to the inlet. The solid blue line is flat. This is because we impose a mass flow rate at constant temperature, and therefore we observe a constant pressure at the probe point number 4, which is obvious. If instead we impose the velocity, then the velocity doesn't constrain the pressure to be fixed, and we'll see the pressure to fluctuate at the fourth probe point. This is what you see in the first graph, in the black graph. The graph on the right is what happens on the outlet, that is 40 meters downstream, and there we observe again the pressure fluctuations in frequency domain, and we compare again the two types of the boundary conditions, and what you see is that the frequency content is different. From this we deduce that imposing a velocity at the inlet creates different types of frequencies in the outlet if you would use instead a mass flow rate. We therefore assume that setting the mass flow rate is the thing to use in this setup. Next question that we wanted to ask is, how do we contain the overall simulation effort in terms of CPU time? And we're wondering about what delta T to use to capture the transient effects. We therefore have chosen two scenarios. One is to use an adjustable time step with a maximum Courant number of 5. Scenario number 2 is to use a max current number of 200. By using 5, we want to capture the transient effects. By using 200, instead, we want to have a larger time step and reduce the computational effort. The question we're asking is, what do we lose by using a larger delta t? And this is what we see. Again, you see pictures of inlet and, sorry, what do we see here is the inlet velocity, the inlet pressure signal at the 4th probe point, comparing the CFL 400 and CFL 5 in time domain left, frequency domain right. What you will see is that passing from Maxco 5 to Maxco 200, two effects seem to occur. That is, we lower amplitude of higher frequencies, so we have a larger signal on the first frequency, and we capture less frequencies. That is, that going from Maxco 5 or a CFL number of 5 to a CFL number of 200 seems to act as a filter in which we dampen the main frequency and leave frequencies out. This can be translated into a signal for the velocity. Again, time domain left, frequency domain right. In black, the accurate Maxco 5. In red, the Maxco 200. Again, we dampen and lose information. And this is the same graph now for the mass flow rate at the outlet, time domain, frequency domain. Same idea. If we increase the time step, we lose information. We can also look at the Q criterion. For instance, to have information about the vorticity structure of the flow. And again, going to a larger time step seems to act as a filter in which we lose information. Here we have a picture of the vorticity. And again, the graph of the velocity. Here you have a summary of the frequency content of the signal, Maxco 5 left, Maxco 200 right. Again, amplitude is reduced. Some frequencies are left out. Then we can ask, what can we do to mitigate the accuracy of Maxco 200? Is it worthwhile to increase the number of outer iterations? Should we switch to a stopping criterion for the outer corrections? Something that we can think about. Or should we instead look at the Maxco 5, a CFL number is equal to 5, and seek ways to increase the computational efficiency of what we currently have by looking at more advanced linear solvers, at more performant middleware, or more performant hardware. And there will be sessions this afternoon that go deeper into this issue. To conclude, I discussed the issue of turbulent mixing in a vertical thermal oxidizer that should be investigated in the energy transition. If we switch to max score 200 or CFL number of 200, computational effort is reduced. However, information is lost, and maybe too much is lost, and therefore we maybe should switch to max score equal to 5 to be able to have a more accurate computation. I'm happy to take questions from here on. Thank you very much for your attention.
Thanks, speaker. Questions?
Thank you. Hi, Domenico. Did you consider at all looking at your temporal scheme? Did you use Euler or backward for this?
We use Euler for this.
So that's first order, so maybe you can get a little bit better accuracy with a higher order scheme?
Maybe we do. The question is that the first thing that we should look into? So maybe we can discuss it further.
Well, just considering that your issue is temporal accuracy, then I would certainly look that direction, right?
Sure, that makes sense. Thank you for your suggestion.
Any more questions?
Okay, you mentioned that you ignore the transonic effect. So there's no convection term in the pressure equation. Does that mean you only solve a Poisson equation for the pressure?
Yes, that is indeed the case.
Okay, I know. Thank you.
Thank you very much.
Any more questions?
Thank you very much for the nice and pedagogical presentation. A side question. You mentioned in your presentation that you plan to share the data.
Mm-hmm.
Are we expecting to have a publication in Open Foam Journal soon?
We could discuss that, yeah, but yes, that's indeed what we would like to do, yes. The short answer is yes. Longer answer is we can discuss how to frame the paper in an ideal way.
Okay, perfect. Thank you.
Any more? Okay, it's time also hits the line. We already have some exceeding the time. Let's thank the speaker again. And that's the end of the session in the morning, and it's lunchtime. Any announcement from outside?
Please follow the volunteers. They're in the white shirt with the red volunteers on their chest. Okay, it's about 5-minute walk, and you probably don't need your jacket. It's quite hot outside. Okay.